SwayamPrabha. Digital India. Educated India.
So we are looking at the root locus. So let's go back and recap what we did, right? So let me go back to this document and then I will come back to this notes file. So if you recall, we did 5 steps, right? So the first step was given an open loop transfer function. The first step was to locate the open loop poles and zeros in the S-plane, right? So and we learned that the root locus will have n branches in general. Each of those n branches will start from an open loop pole and they will end at an open loop 0 if it exists, okay, and the remaining n minus m branches will go to infinity along asymptotes, right? And then we figured out how to get the parts of the root locus that lies on the real axis, like we use the angle condition in that regard, right? So we only looked at the real axis and we divided the real axis into subregions based on the location of open loop poles and zeros. In each subregion you take a test point and you look to the right of the test point. If the number of real open loop poles and real open loop zeros is odd, then that region lies on the root locus, right? That's the second step. The third step was to determine the asymptotes of the root loci, and using the angle condition, once again we figured out that the angle made by the asymptotes with the real axis is going to be plus or minus 180 degrees times 2k plus 1 divided by n minus m, right? So what are asymptotes? Asymptotes essentially indicate the locus of the closed loop poles as essentially the k tends to infinity, right? In case there are no open loop zeros where we can terminate that branch, right? So and the point of intersection of the asymptotes on the real axis is essentially given by sum of open loop poles minus sum of open loop zeros divided by n minus m, right? That was step 3. Step 4 was to figure out potential breakaway or break-in points. We discussed when breakaway and break-in points could occur, and we figured out that at a breakaway or break-in point we are going to have a repeated pole, right? So if a polynomial has a repeated pole, like then what we do is that we take the first derivative, even that value or root like satisfies the first derivative equals 0. That's the concept we use to figure out how we could get breakaway and break-in points. And the next step was to figure out the angle of departure from a complex pole or angle of arrival at a complex open loop 0, right? So we figured out this is the formula. So we did an example yesterday, right, to essentially see how we can calculate, right? So please note that step 5 applies only when we have a complex conjugate open loop pole pair or complex conjugate open loop 0 pair, right? So if we in the example that we just started off with, like there are 2 open loop poles, both were real, right? So step 5 did not apply to that problem, right? Step 6 is what we are essentially going to look at today, okay? And then we will complete the root locus construction, right? So what is step 6? Step 6 is to determine the crossover points, okay? Like what are these crossover points? Crossover points are nothing but points where the root locus cuts the imaginary axis. So imagine that like in the S-plane, the root locus essentially we want to figure out where it cuts the imaginary axis. And why are these called crossover points? Because I can have, for example, let's say 2 branches of root locus coming like this, and then they cross over from the right of plane into the left of plane, right? So please note that the imaginary axis divides the S-plane into RHP and LHP, right? So a crossover point, as the name indicates, is a point at which the root locus transitions from one half plane to other. It can be either from right of plane to left of plane or left of plane to right of plane, okay, either way. So, but we can immediately see that the imaginary axis is the boundary, right, between the 2 half planes. So that's why, you know, like we are looking for where the root locus cuts the imaginary axis. Okay, those points are what are called crossover points. And how do we figure those out? You know, like by substituting S equals j omega in the closed loop characteristic equation. Why? Because if any branch of root locus cuts the imaginary axis, which includes the origin, by the way, right? So then what's going to happen? The real part is going to be 0, right? On the imaginary axis, that's what it is, right? So if you consider a complex variable S of the form sigma plus j omega, if the complex variable is purely imaginary, that means sigma is 0, right? So that's why we search for roots of the form S equals j omega for some value of k, right? That's what we are going to look for. So that's why we substitute S equals j omega in the closed loop characteristic equation. So let's consider what example that we are looking at. For the example that we are looking at, g of s h of s was k divided by s plus 4 times s minus 1. I just expanded it as s squared plus 3s minus 4, right? So now the closed loop characteristic equation is this, right? 1 plus g of s h of s equals 0. That's something which we already know, right? So we just plug it in and simplify, we get the closed loop characteristic equation as s squared plus 3s plus k minus 4 equals 0, right? Now we substitute s equals j omega into this particular equation, right? So this is the closed loop characteristic equation, right? Because please remember, the roots of this closed loop characteristic equation are the closed loop poles, right? So we are looking for closed loop poles which are pure, what to say, imaginary. So we essentially basically substitute sigma, the real part, to be 0. So the structure is of the forms j omega. Okay, omega can be 0 because we can also have the crossover point of the origin, right? See, for example, we can have a crossover happening from the positive real axis to the negative real axis and vice versa. You can have crossover on the real axis also, right? So we substitute s equals j omega, s squared becomes minus omega squared, then we get 3j omega plus k minus 4. Then we collect the real part and the imaginary part. So the real part is minus omega squared plus k minus 4, imaginary part is 3 omega, right? So obviously when both are equal to 0, right? So when this complex function is equal to 0, the real part should be 0, the imaginary part should be 0, right? So real imaginary part being 0 gives me, from here I can immediately figure out omega is 0, right? That's the only potential, that's one potential solution for omega, right? A crossover point. But once again we need to check the value of k, okay, whether it's positive or negative, right? So what do? We check, now process the real part. So if you look at the real part, if I substitute omega equals 0 in the real part, what happens? I get k minus 4 equals 0, or in other words k is equal to 4. So omega is equal to 0 and k equals 4 is a potential solution of the closed loop characteristic equation when we are searching for a crossover point, right? And this is a valid solution for this problem because k is assumed is taken to be positive, right? So you see that omega equals 0 means s equals 0, right? That means the origin, right? So and at that point the value of k, the gain k, is positive, right? So the origin is a valid crossover point, right, as far as this particular example is concerned, correct? So so that's step 6. Okay, is it clear how to calculate what is meant by a crossover point and how do we calculate them? And why are we interested in crossover points? Because a crossover point indicates when I am transitioning from one half plane to another, right? Is it not? Because that's very important for us as far as stability is concerned, right? See, I have to design my closed loop system such that I choose only those values of k which would stabilize my closed loop system, right? So a crossover point represents when the root locus may transition from the right of plane to the left of plane, which is coming from unstable to stable regions, or vice versa, right? So I know which ranges of k to choose, which not to choose, right, for closed loop stability. Is it clear? So that is step 6, okay, determining the crossover point. So the final step is to sketch the root locus, okay. Like by and large what we need to do is that like we need to essentially do steps 1 to 6. What I expect of you when you draw the root locus by hand is to methodically do steps 1 to 6. By that time you will have an idea, as you keep on constructing root loci, you will have an idea as to how to construct the final root locus approximately. The final step is to essentially consider a set of test points on the broad neighborhood of the origin and the imaginary axis in the complex plane and sketch the root locus, which is not very tractable or very easy to do when we do by hand, right. So when you, for example, if you use a software like MATLAB, you can pretty easily get the actual root locus. But here, like we will just use steps 1 to 6 to essentially plot the root locus, okay. Is it clear? And once again, like please use the rlocus command, okay, in MATLAB to sketch the root locus for all the problems that we are doing, right. Even in homework number 2, which I have given you, like you need to construct root locus for certain problems. Sketch by hand and then just check your solutions, okay, by plotting the root locus in MATLAB, right. So let's construct based on whatever we have learnt, right. So we already know that one branch of the root locus is going to start from -4, okay. So we are always going to have the root locus to start at an open loop pole as k tends to 0. So one branch of the root locus starts from -4 and another starts from +1 in this direction, and of course there is a crossover at 0, okay. At the crossover point, see, you need to mark all the important points, okay. At the crossover point the value of k is 4, right. And where do these 2 points intersect? -1.5, right. So that was the break away point, right. So let's say I have -1.5 to be somewhere here, okay. So what's going to happen is that they come here and then they intersect each other. And what is the value of k at -1.5? If you go back to step 4, at the breakaway point, what was the value of k that we calculated? So it was 6.25, okay, that is what we can see, right. So it was 6.25, so we need to essentially mark that, okay. Now they are going to break away, okay. Now the question is that like how does this evolve with time, right. So and we know that the asymptotes are going to also intersect at -1.5 for this problem, okay. Please note, I am repeating once again, in this particular problem it so happens that the point of intersection of the asymptotes on the real axis and the breakaway point happen to be the same, okay. It is not the case in general, okay. So in this case the asymptotes also intersect at -1.5, and what are we going to have as the angle of the asymptotes? +90 and -90. So what we will have in this problem is that one branch will just take off vertically upwards, okay, and another branch will just go vertically downwards, okay. So this is what happens as k tends to infinity, okay. This is how you should mark the root locus and mark all the critical points and so on, right. So that's the complete root locus for this particular problem, okay. So using all the steps, have we used all the steps? Yes, right. We have marked all the critical aspects of the root locus, and immediately we can see from the root locus is that the closed loop system is stable for all k. When is the closed loop system stable? K greater than 4, right. Why? Because you see that one branch of the root locus is always going to be in the left of complex plane, okay, the one starting from -4, okay. But another branch which starts from +1 migrates into the left of plane only after k is greater than 4. So you need both all the closed loop poles to be in the left of complex plane, right? So the root locus gives you a very nice graphical representation to essentially figure these things out, right? So that's the advantage with the root locus, right? You can get a general perspective, okay? So let me ask you another question, okay? So what range of k would, see, closed loop stability is for k greater than 4, okay, would provide a settling time, of course using the 2% criteria, okay, less than 4 seconds. So from the root locus, can we figure out, you know, like what ranges of k would give me a settling time of less than 4 seconds? So what was the expression for the settling time? No? Ts was 4 divided by zeta omega n, right? So that should be less than 4, or in other words, zeta omega n should be greater than 1, which implies that minus zeta omega n should be less than minus 1, right? So let's say I draw a vertical line at minus 1. See, we already discussed this, right? When we last week, you know, when we wanted to get the how to translate performance specifications into regions of poles, right? So you see that any if all the closed loop poles lie to the left of this vertical line at minus 1, that will give me an assurance that the settling time is less than 4 seconds, right? Now, what value of k would get me that? Obviously, what I need to do? I need to find out what is the value of k at this point, right? How do I find what is the value of k at that point? No. I look at the closed loop characteristic equation, right, and substitute s equals minus 1, right? So that's why, you know, we are doing all these steps, right? Look at the closed loop characteristic equation, right? What is the closed loop characteristic equation? S squared plus 3s plus k minus 4 equals 0, right? Substitute s equals minus 1. Why am I doing it? Because that is the point after which, beyond which, you know, like the both branches of the root locus go to the left of the minus 1 line, right? So when I substitute s equals minus 1, what do I get for k? This becomes plus 1, this is minus 3, minus 7, then I will get k to be, what is the value of k? 6, right? So 6 is, okay. So for any value of k, which is greater than 6, right, you will get a settling time less than 4 seconds. Okay, so that's the guarantee we can have. Okay, of course, please note that we are using the expression for the step response of an underdamped second order system to come up with the settling time response. Okay, please remember that. Okay, so this is essentially assuming that, you know, like you are going to design an underdamped second order system by and large. Okay, we need to keep those things in mind, right? So when we do such analysis, right, but at least like it gives us a first cut value beyond which we can go and tune our experimental system. Okay, so that's the benefit of this analysis. Okay, so this is the final root locus plot. Okay, is it clear? Okay. So any questions on this? Right. Okay. So now what we are going to do is that, like, I am going to do an example. Okay, like another example, and then we will quickly run through all these steps. Right. So let's do another example for a root locus. Yes, please. Yeah, okay. See, at what point of the in the root locus there's both root locus branches, you know, lie to the left of this -1 vertical line. At that's why, because that's the condition that we obtained, right? Okay. We discussed this last week also, right? So that is for settling time condition, we converted into a constraint on the real part of the pole. See, please remember what was minus zeta omega, it was the real part of the poles of the underdamped second order system, right? Okay. So essentially we want, if our dominant dynamics is going to be an underdamped second order system, we want the, the real parts to be to the left of this -1 line. Right. So I think we did it last week, right? So sometime 2 or 3 classes ago, but then like we need to take it a pinch of salt, right? So because see, between k equals 6 and 6.25, the system is really overdamped. Okay, it's not yet underdamped. Please remember, right? So, but then you know, like we still use this analysis to get an approximate range. Okay, that's what we are doing, right? But the root locus will tell you that. Okay, by and large, we want to design an underdamped system. So I would choose maybe a k beyond 6.25, okay, in this example.
But how do you understand that between 6 and 6.25 it's
Overdamped, right? Why? Because between 6 and 6.25, what can you say about the two branches of the root locus? Both are on the real axis, right? So both closed loop poles are going to be real. So what do you call a second order system where both with distinct real poles? Overdamped, right? At k equals 6.25, it becomes critically damped, and then k beyond 6.25, it becomes underdamped. Okay, that's what we can easily look from the, see, so now you can appreciate the value of root locus, right? It gives you a graphical representation from which you can get all these interpretations, right? Yeah. Value to the left of the breakaway point, it goes from 0 to 6.25. So you pick any value of S, you substitute it here, you will get the corresponding value of K, right? See, you are asking about this range, right, from -4 to -1.5. It scales the same way as 1 to -1.5, right? So please note that, you know, another interesting thing about the root locus is that the root locus plot doesn't scale linearly with K. Okay. See, for example, you know, like as we construct more examples, you will see that to travel what we think is a very large distance, the change in k would be very small, relatively smaller, right? And sometimes, you know, like we are going to do another example where you will see that in a very finite distance, you know, it would go from 0 to infinity. Okay, it depends on the problem, right? So it doesn't scale linearly, you know, like as you vary k, right? Yeah. Fine. Any other questions? No. So I'm going to leave you with 2 questions, right? So question 1, okay, you think about these questions and then like we will answer them in the next class, right? So what happens when k is negative? See, in general, my k can go from -infinity to +infinity, right? Do you agree? Right? See, k is a design parameter, you know, like k is a real number, so I can have k going from -infinity to +infinity. See, think of k, let's say, as a proportional gain, right? It's a real number. Okay, we did only for the part going from 0 to infinity. What about -infinity to 0? How do you construct the root locus for that? Okay, what steps will change? Anyway, I have given those changes in the document. Please read through them, think, and then come back to the next class. We will discuss them once again, right? And question 2, what would happen with positive feedback? Okay, that's the second question we need to ask ourselves. So we looked at negative feedback, but let's say if we are doing positive feedback, right, in some example, some case, right, how would the steps of the root locus change once again, right? Please think about it. Why would With positive feedback, why would the root locus steps change? Because the closed loop characteristic equation is going to be now 1 minus g of s h of s equals 0, right? We did everything considering 1 plus g of s h of s equals 0. Then the magnitude condition will remain the same, but the angle condition will change, right? Okay. So, so you think about what changes would occur, right? Is it clear? Okay. So please think about both these questions. The answers have already been provided in the handout. I just want you to read and think and come back to the next class. Is it clear?